cells are in the egg box mode, as you can see here. And you come, and this here is a transition point, and then all of them are going to switch.
Good afternoon. My name is Bill Spencer, and I'm delighted to welcome you to the Spring 2023 Newmark Distinguished Lecture. Our speaker today is Professor Glaucio Paulino. He was on the faculty here for quite a few years. When I came here, he was already on the faculty before he moved on to Georgia Tech. But I wanted to tell you that it's particularly a pleasure to have him here today because he was my next door neighbor for all those years when he was at the University of Illinois. And he is the person who started the Newmark Distinguished Lecture Series nearly 20 years ago. And so it's great to have it circle back and to have him in there. Now, we're broadcasting this lecture both on Zoom as well as we have it here today live. For those online, if you have any questions, please put them in the Q&A section of the Zoom meeting, and we'll do our best to make sure that everyone has their questions answered by Professor Paulino. Before beginning, let me just tell you a little bit about Professor Paulino. He started his academic career in Brazil with his master's and bachelor's degree before moving to Cornell University, where he got his an additional master's degree and his PhD in theoretical and applied mechanics and civil engineering, respectively. Professor Paulino has seminal contributions in so many different fields. As a matter of fact, it was difficult for him to decide what he was going to present here to our group today, from things ranging from the development of methodologies to characterize the deformation and fracture behavior of existing and emerging materials. Topology optimization for large-scale, multi-scale, multi-physics problems. Indeed, the work that my group has done on topology optimization was inspired by Professor Paulino. Additionally, variational methods and deployable and adaptive structures, and the topic for today, origami engineering. Professor Paulino has won numerous awards for his achievements, from the Daniel Drucker Medal from ASME, the Menlin Medal from ASCE, the Reddy Medal, the Origami Medal, and in particular, he is a member of the National Academy of Engineering, recently elected. So I'm going to welcome Professor Paulino. We have to get things switched around a little bit, but let me bring him up and let's give him a round of applause. I need to share the screen here. I need to stop sharing. You're good. That's what we're seeing.
Thank you, Bill, for your very kind introduction. Good afternoon, everybody. I am very happy to be here today. As Bill said, I was a professor here for so many years, and I used to be his neighbor in the Newmark lab, and I am very honored today to be delivering the Newmark lecture. So, today, It has been a very pleasant day, very good memories. I see Professor Reza here, very good to see you. And I had very good meetings, and I can see some of the students here that I visited. I visited Shelley Zhang's class today in structural analysis and Professor Oscar class in finite elements. And very interesting, those are the classes I used to teach long time ago. Today, I am going to talk to you about some recent work that we did on origami engineering, and maybe an alternative title for the seminar will be Engineering Origami, how to engineer origami, how to obtain reconfigurable, deployable, adaptive structures, and how to do that through origami. And before I go on, I would like to acknowledge all the collaborators that I have in what I'm going to show you. That includes Evgeny Filipov, Tom Hirutashi, Espinosa, Siridar, Krishnasamy, Diego Miseroni from Trento, Chris Liu from Caltech, now at the Peking University, Pradeep Pratapa, Larissa Novelino, Jamie Wei, Nicholas Alderet, and Salman Lin. And the sponsors for the work, mainly NSF, JSPS, and the Raymond Alan Jones Chair at Georgia Tech. Origami has been used in many areas. Origami is pervasive. You just think about any area, and you can see that origami can have an impact. Has been used a lot as an art form, entertainment, in the fashion industry, and one area that I like a lot, education. After the lecture, if you Google Origametria, you can find a wonderful technique to teach mathematics for children using origami that was developed by Miri Golan in Israel. I will go back to origami as art. This is one of my favorite pieces of origami. This is the orchestra by Eric Joacel. These are, if you count, there are 11 musicians, and here there are 22 pieces of paper folding on. You have one piece of paper for each musician and one for each instrument. If anyone goes to Japan, I strongly recommend to stop by the Origami Gallery in Japan so that you can see at least part of this work of art. And another one that I would like to share with you is the Dragon model by Satoshi Kamiya. And this is one piece of paper, folding on, nothing else. One piece of paper folding on. And you can see where we have reached. You can see how beautiful this is, and the level of detail of the head, the horns, the feet, the claws. And here we have even the scales to get it to be more realistic. The pattern is not symmetric, but the compound pattern produces a symmetric model. This is also in the Origami Gallery in Japan. But now, coming to engineering, when we talk about engineering, some of the words that come into mind are compact, deployable, prefabricated, self-assembly, tunable, multifunctional, adaptable, and many of those relates to applications in civil engineering and other applications, robotics, biomedical field, and so on, that we have here. And whenever we talk about origami, we have to think about elements of theory and analysis, the mathematics, how to understand the behavior, the models, and also the design. Design is very important. For example, here you can see the Stanford bunny, but then, for example, you need to do the crease assignment, and this is a very complex task. And after you do the crease, you have to decide about mountain valley assignments. From a computer science point of view, this is a very hard problem. Also, one area in active development is thickness accommodation. All the theorems I know in math, they have been approved for thickness in the limit of the thickness going to 0, but in reality, in engineering applications, the thickness is finite, and this introduces a lot of complications in the process. And then we have to talk about materials and fabrications, and for example, the kind of connections, joints, and kinematics, and so on. And we are going to address a few of those elements during the talk. Some time ago, I worked at the NSF as a program director, and over there we created this, we helped to create this program called ODC. That means Origami Design for Integration of Self-Assembly Systems for Engineering Innovation. That was part of the EFRI, Emerging Frontiers in Research and Innovation, and consists of using math and fine arts and the interplay between the two, together with design theory and active materials to achieve origami and adaptive morphing systems. And the main areas were compliant mechanisms, active materials, bio-origami, DNA folding, protein folding, and so on, and foldable structures and microstructures. And since then, this was around 2011, 12, and since then, there has been a tremendous amount of development in the field of origami in engineering applications, especially in the US and around the world. Origami has 4 basic mathematical rules. That's it, 4 mathematical rules. And if you think, for example, in the field of quantum mechanics, you have specific rules, but they govern the entire field of quantum mechanics, the entire field of chemistry, and so on. And similarly, in origami, we have these 4 rules. So that to achieve flat foldability, it has to satisfy the 2-polarability, and I am going to elaborate more on this. It has to satisfy the Maekawa theorem. I am going to elaborate on the Kawasaki theorem, and the folds should not interpenetrate for physical reasons. And it is the same mathematical rules that lead to engineering innovation. For example, I have an origami that is flat foldable. Then this is one of the most famous pieces of origami. This is the Chris pattern for the crane. And then you can see that I can do it with 2 bowlers, okay, with the bowlers repeating themselves. And when I fold, I achieve this great result, right? That you can see here. And we can show that the creases associated with the flat foldable origami, they are Eulerian graphs, and Eulerian graphs mathematically we can prove that they can be colored with 2 colors. Another important result is the Maekawa theorem. And that was looking for a piece of paper. Is the Maekawa theorem. What the theorem says is that if you choose a vertex anywhere, and if this is to be flat foldable, for example, you can fold this as many times as you wish, okay? And it's guaranteed by Maekawa theorem that when you look at this, the difference between mountains and valleys has to be 2, no more, no less, 2, and only 2. And then, for example, here, you can count. This one I just did. You have 1, 2, 3, 4 mountains and the 2 valleys. The difference is 2. Okay, and you can try this by yourself. No matter how complex the origami is, this has to be satisfied. Another idea is that if you pick up the vertex and just number the angles in sequence, then you can see that all the odd angles add to pi, add to a straight line, all the even angles add to a straight line. And we should have no interpenetration of folds. And it is this same ideas that recently we introduced in an origami engineering class that I taught at Georgia Tech and also at Princeton last year. And one of the ideas is to use Legos, for example, to illustrate the mathematics. Here you can see the key idea of the Lego. We were inspired by a toy in Japan, but then we generalized all the angles of the parallelogram, and we printed hundreds of thousands of those Legos, and then you can see here the key idea of these connections here, so that it can allow us to play with the Legos and reassemble the origami. And here is Larissa, for example, making mutative with the Legos. And for example, so I am going to talk a lot about the Miura configuration, that is this configuration that you see here, and about the egg box configuration, that is this configuration that you see here. And in the class, for example, the students, they have to play with the Legos, and then you can see here that if you assemble them in this way, you get a Miura, that way you get the egg box, and maybe very quickly here, I could give a demo, and they do this in class, for example. And here we are building the neuron, and we put them together here. And then, for example, also at the same time, I go and derive all the mathematical relations, all the parameterization, all the kinematics, all the behavior. But then they experience that math in different ways. With the language, for example, they have to do paper foldings. We will get some of these in class. They have to do it in real time. And then, as you can see here, there is only one unit. Here there are many units, but then in class, for example, they are going to cooperate among themselves, and they have to do this correctly. For example, we are going to study the behavior of the row neuron that is quite different from the column neuron, and we learn the mathematics that governs those relations, and then they learn about the tessellation. Then, for example, here, to do, let's say, a 2x2 pattern, a student sitting where you are, you have to collaborate with your neighbor in the row, and then the neighbor in the column, and then to do the tessellation, to cooperate everybody. And you have to understand things in order to do it correctly. And this also helps to understand the math. For example, Miura is developable. Then you know that this can be done with a single piece of paper, as you can see. And this is Murphy's law. Shelley told this to me, and I forgot. Thanks, you. Appreciate your help. Thank you. And then we can come here. If you just change this a little bit, Miura is in general the most famous developable pattern. If you just change this a little bit, and then we assemble this in this form that you see here. And again, the students do that in the class in real time. And then this is the egg box that resembles this pattern. And again, I already explained here is one unit. This is with the Legos. Here is with the paper, with the tessellation. And again, the students will collaborate doing that. But then, for example, we show that mathematically that this is not developable. This means the egg box cannot be done with a single piece of paper. If you try to do it, only if you destroy it, it's not possible. Okay. And I'm going to share this with you. As you can tell, I'm very excited when I teach this class. And then at the end of the class, there is a trade show, and the students go, and there are students in general. I have students from the entire university, from engineering, math, physics, and so on. And the groups are intellectually diverse. They cannot have more than 2 students from the same major working in the projects. And then you can see here interesting project like this. A group here was in bioengineering. They did cast-gami, something inspired by origami for casting, so that is more comfortable for the patient, an origami resistor, orilight, shelters, and so on. So now I would like to share with you some work that we did recently on metamaterials with reprogrammable frustration. Sometimes frustration can be bad, especially in life, but sometimes, especially in engineering, frustration can be good. And I will explain how we can use frustration to design reprogrammable metamaterials. And most of what I am going to tell you, you can find in this paper that was published recently in Advanced Materials. And here is the big picture of Frustration lines that are kind of defects or point defects, like line defects or point defects. Okay, and then now coming back, since we are going to have a lot of, we are going to concentrate in this lecture mainly in these two patterns that I just illustrated, the Miura and the egg box. The Miura is very interesting because we can show that it has a negative in-plane Poisson ratio. When you shrink in one direction, you shrink in all the directions, as you can see here, and has a positive Poisson ratio out of plane because it forms this saddle type configuration when you bend. The egg box is the opposite. It has a positive in-plane Poisson ratio like any other material, as you can see here, standard materials like wood, metals, and so on, and has a negative out-of-plane Poisson ratio. And you can see here, this is an egg box. If I try to bend, you can see that it forms a dome. I don't know how well you can see, but it forms a dome, all right? You can see it. All right, so, what happened is that the reason I'm showing you all these patterns and the tessellations is because they are periodic systems. They have a tremendous amount of symmetries, and they have very beautiful geometrical properties. And that this beauty in the geometry translates into beauty in the mechanics and into the geometric mechanics of the pattern. For example, regarding the Miura, group in Harvard parameterized it, did a lot of math to derive analytical expressions for the Poisson ratio in bending and in stretch. If you just take a look in these expressions here, pay attention, they only differ by the sign, same magnitude. Later, a group in France did the same derivations for the egg box, and then they found the Poisson ratio in bending and in stretch. Pay attention, same magnitude, only a sign difference. And one key idea is the following. In what I have shown, you have seen that we have two different materials, and you can see here, Miura is Miura, egg box is egg box. The question is, we have these great properties of each of these materials in the same material system, and the answer turned to be yes, and that's what we did with the morphic material. Now, if you take a look here, I just programmed, I didn't bring the morph, but I just programmed all the units in the Miura mode. And then if you look here in the animations, they will behave exactly as the Miura pattern that you have seen before. And now if I program all the units in the egg box mode, then they will behave in a similar fashion to what we have seen before, but now it's a single material system. And then what we did was to do all the math to see if we could derive analytical relationships for the Poisson ratio behavior. And in a stretch, this is the expression that we got in the red box. And in a similar way, like in the stretch, we do the negative of the ratio of deformations. For the bending, the definition is that it is the negative of the ratio of curvatures. And when you look at the final expression, again, you can see that they differ only by the sign. So this is a tremendously elegant result that we have been trying to get a better and better understanding about it. And some of these derivations that I have shown you can be found in a recent paper in PRL on geometric mechanics of origami patterns exhibiting Poisson ratio switch by breaking mountain and valley assignments. And recently, we summarized our understanding in this paper in PNAS on discrete symmetries that control geometric mechanics in parallelogram-based origami. Okay. And just to summarize this, then we have here in this design space, the angles of the pattern that are alpha and beta, and if all of them are equal, then it's an egg box. If they are alpha and pi minus alpha, it's a Miura. In plane, we have seen that the egg box has positive Poisson ratio, the Miura has negative, but the morph, you can actually switch, okay? And now when we look at, here is our parameterization of the pattern, and here is the PC angle, the phi angle. We are looking at the geometry, and this pattern is dictated by these angles alpha and beta of the morph pattern. They are all equal, as I said, is in an egg box. If they are pi and alpha and pi minus alpha, then they are a Miura. So we can do the derivations here in terms of expressing this angle PC in terms of phi and the angles of the pattern, and we can derive this analytically and get the expressions that we have seen here, and we can look at this configuration space, the angle C versus phi. What we can see is that, for example, to the right of the gray line, then we are always in an egg box mode. Here in gray is a transition region, and then here will be a Miura mode. And then, for example, if I pick up this line here, the purple alpha 60, beta 40, I start here with an egg box mode. There is a transition phase, and then I transition to the Miura. And then I can get, for example, in a tessellation hybrid modes, okay, as a result of kinematic bifurcation. And this is what you see in this animation. Here, all the cells are in the egg box mode, as you can see here. And you come, and this here is a transition point, and then all of them are going to switch to the Miura mode, as you can see here, and and now we go back. And they don't need to be all equal like before. Then I can go to a hybrid mode where I am going to have some units that are egg box and some that are Miura. As you can see here, that the endpoints, they transition to an egg box, and the central one to the Miura. And we can use this, for example, now to design metamaterials. For example, I can put all the Miura units, program the material on the left, to be on the left, and the egg box on the right. And if I bend, this will bend in more or less in this way that you can see here. Then on the right is very typical of the bending in the egg box, and on the left, very typical of the bending in the Miura that we have seen before. And there is a transition in between, or I can alternate them, as you can see here. And then when this bends, it will bend in this way, or I can do any combination that I wish. We wanted to do some experimental validation for this work, and we used 1 millimeter thick polypropylene sheets that were milled with a CNC. That you see here. And a big problem in doing the experiments, they are illustrated here. When you try to grip the system, then as we know, this will form, for example, with standard grippers. When you grip here on the left and right, this is a dot bond shape. And this is very undesirable and very difficult to get meaningful results in the testing, because we get essentially non-uniform transverse deformation, and it's very difficult to find a good region where we could do the measurements, or we have to use very large samples. And then the key idea is, can we redesign these fixtures so that we can eliminate or minimize this problem? And this is what we did here in this paper last year in experimental mechanics letters. And the key idea then is, instead of using these standard fixtures that you see here, then we have a special railing system that has several components that allow us to minimize all the friction in the device, and also has some desirable desirable features that will allow us to do these experiments. And when you take a look here in the general deformation, you see with the standard fixture, we have this very bad behavior here with the dog bone, but with the Sambenan fixture, the redesigned one, then we can get a very nice region with uniform transverse deformation, and then we find a way to test the periodic system, especially using small samples. And what I want to show you now is how this behaves. And let's program the material, for example. Let's start with all the units in the egg box mode. So there is no Miura unit. And then you can see here, the red is the theory, and the blue are the experiments, and the yellow I am going to show you are the simulations we did with our Merlin software. And you can see that the behavior is quite nice, and as expected, we have a positive Poisson ratio there. And now we are going just to change one of the units here to be in the Miura mode. And you see, since the egg box dominates, then it's still positive Poisson ratio, but a different range, and the three sets of data, they match quite well: the experiment, the simulation, and the theory. Finally, not finally, almost there, we have two Miura units now. And these are the results that we get. Something very interesting for a very large range of behavior, as you can see there. The Poisson ratio is very close to zero. And then after some time, you are going to see then it changed to negative Poisson ratio. And finally, with all the units in the Miura, we have 0, 1, 2, and 3. And then the entire range of the Poisson ratio here will be negative as we expect. Okay, but with the morph, we are only creating hybrid modes in one direction. And the key idea is, can we do this in more than one direction? And then we did this with the trimorph pattern that is illustrated here. And these are, for comparison, I put here the Miura, the egg box, and the trimorph. Now, when we look at the vertex, then we are going to have three sets of angles. These ones are alpha, and these alternate ones here, alpha plus delta and alpha minus delta. And here is the geometry of the pattern, and this pattern is in a triplanic space. It's not in a Cartesian space. That means these eta angles here, they are not necessarily 90 degrees. And this is the schematic of the pattern. Here, alpha are the panel angles. This is alpha plus delta. This is alpha minus delta. And we color them here so that you can make the references. We number this 1, 2, 3. This is 4, 5, 6, 7, 8, 9. And gamma here, our notation is that gamma are the dihedral angles, the angle between the two panels, the two different colors. And then we have gamma 1, 2, 3, and 4. And we can, again, derive analytically the relationship between these angles here, C and phi, and we get this relationship here that is very beautiful. And you can see that it's a symmetric relationship, and these parameters C, B, and D, for example, they can be obtained as a function of the geometry of the pattern. And then we can look at the configuration space. Now, when we take a look here, we are going to look, this is the C versus phi, and then I have here three types of modes. We have first one type of Miura that you can see here if you pay attention to the colors. This here will be an egg box mode, and this will be another Miura mode. Okay, and if we look here, for example, at the alpha variation, when alpha is 90 degrees, for example, then we can see that the green disappears. There is no green in this last curve here, and then this becomes the Mareto-Vars pattern. And if we look here at the delta variation, for example, and then when delta equals 0, there is no yellow, there is no blue, then it's a pure mode, egg box mode pattern. And then the pattern can transition among all these modes. And then we wanted to connect the math of the spherical trigonometry and the programmable states of matter. We have these 3 states, one type of Miura, another type, and the egg box. And these are the spherical polygons. And here we have the Gauss map of the 3 characteristic modes of the trimorph. As we expect, for example, the egg box is a spherical quad in the Gauss map, and the Miura is always a bow tie, but you can see that they are in different orientations. This bow tie here is in the vertical orientation, and this one in the horizontal, because they are 2 different modes.